A comment on my previous video made me revisit the idea of logarithm space, and I discovered some very pretty diagrams that I wanted to share. Here's a diagram of z adjoin root 2 under the canonical embedding, f1 on the horizontal axis sending root 2 to root 2, and f2 on the vertical axis sending root 2 to minus root 2. In my last video I defined maps L1 and L2, which were log of the absolute value of f1 and f2 respectively. And I defined L of x to be the point with coordinates L1 of x and L2 of x. So, I applied L to the units in z adjoin root 2. But what happens if I apply it to everything in this diagram, not just the units? Well, let's make some simplifications first. We've seen already that L of x and L of minus x are the same point, so to avoid that redundancy we might as well only consider the top half of this diagram. I'm also going to exclude the origin, of course, because you can't take the logarithm of 0. And now I'm going to colour the left and the right halves different colours. And now let's apply L. Well, this looks pretty chaotic, but the advantage of log space was that our hyperbolas of elements of fixed norm turned into lines. So let's draw them back in. Here they are. The line through the origin is the line of all points of norm plus or minus 1. The line next to it is all points of norm plus or minus 2, then plus or minus 3, plus or minus 4, and so on. Let's rotate this picture for a clearer view. As we predicted last time, the points of norm plus or minus 1 form a one-dimensional lattice. But notice that a similar structure is repeated on every single line here. Some lines just have a simple lattice, whereas some lines have a couple of lattices next to each other, and some lines may have nothing at all. Right? This whole picture is periodic, it has translational symmetry. In group theory terms, the unit group acts on this whole picture by translation. Let's have a closer look at the norm plus or minus 3 line. We can see that there are no elements here, no elements of norm plus or minus 3. That means that the element 3, the number 3, which has norm 9, can't be the product of any two elements of smaller norm. If it was, it would have to be the product of two things of norm 3. So the number 3 has no non-trivial factors here. And since z adjoin root 2 has unique factorization, that means that 3 is prime, a prime element in z adjoin root 2. In other words, the prime 3 of z remains inert when passing to z adjoin root 2. Okay, what about norm plus or minus 2? Well, we can tell that, for example, there's a single element of norm plus or minus 2, up to multiplication by units, so when I square it, I must get a unit times something of norm 4. But up to units, the only thing of norm 4 is the element 2. So, if I ignore the units, 2 must be the square of some element of smaller norm. In other words, the prime 2 in z is ramified in z adjoin root 2. It's the square of a smaller prime. That's no surprise. 2 is the square of root 2. One more example. Let's look at norm plus or minus 7. Here there are two distinct elements up to units. And it's easy to see that multiplying them and ignoring the units must give you the element 7 of norm 49. This tells us that the prime 7 in z splits in z adjoin root 2. It's the product of two distinct smaller primes. Finally, I'll leave you with this picture to show you how regular this image is along lines of divisibility. Here are all the lines of norm plus or minus a power of 2. And here are the lines of norm plus or minus a power of 3, plus or minus a power of 5, plus or minus a power of 7.